Hi, this is a video to look at the Raphson method for root finding. We're looking for x where f of x is equal to 0, where f of x is a function of x. So let's start off with a picture of a function. So on the horizontal axis we have x, on the vertical axis we have f of x, and if we have some function like this, then what we can do to start with is guess some sort of value for where it crosses. So we're going to call this first guess x0. And we see that x0 is not actually that good a value because it's up here. But in the Raphson method, what we do, I probably use a green line. I'm going to try and draw this now. What we do is measure a gradient at the point there where it touches the axis. And in effect what we're going to do is go down this gradient to find where it crosses the axis, to find a new point here, which we'll call x1. And from there we repeat the process. We can go up and see what the value is here. And now I'm going to struggle to draw this, but we can imagine having some sort of gradient like this. And our next guess for x2 is really going to be so close that really I cannot draw it anymore. Okay, so this is a sort of diagrammatic representation of how we find a root. We start with some guess, which in this case was x0. We've gone to find the value of fx0 there. And we've gone to find the next value of x1. And from that we've got an improved estimate of x2. Okay, so let's examine this in a bit more detail with another diagram. So if our function is like this, now this is our axis, and I'm going to say our first guess is here at x0. Then we have a sort of triangle here. Again, I use green for the gradient. So this is a tangent with gradient of f primed of x0. It's if we're finding the gradient of a function, I'll just label this again, f of x, and this is x going along here. If we're finding a gradient of a function, what we can do is differentiate the function and then pop in the value of x and the gradient function will tell us what we need to know. So now if we look at this triangle here, now the height, this height here is f of x0. This length here, well, this is our next guess, which is x1. So this length here is going to be, well, I am going to write it as x1 minus x naught. And I might come to regret that later. It's going to be a negative number, but we'll just leave it like that for the moment. It's the difference in positions, and the way that I have drawn it there is it's sort of the difference in positions measured in this direction. Well, or sort of we're going from x0 to x1, so actually that's going to be a negative number, the way that I've drawn it, because it's going backwards along the x-axis. Okay, now the tangent gradient is this, f prime of x0, but that gradient is also equal to the height divided by the length. So we know that if we're measuring any sort of gradient, then if the gradient here, well, let's say the gradient here is 4, then this length here might be 6, and this length here might be 1.5. Or if we use letters, we can say that this is A and this is B, and so the gradient is equal to A divided by B. Okay, nothing too controversial there. So what we have now, we can rewrite that for the gradient f primed of x0 is equal to f of x0 divided by x1 minus x0. And we can rearrange that expression. So the x1 minus x0 we're going to take to the top and put the, so what we can rearrange that to is x1 minus x0 equals f of x0 all over f primed of x0. Now I'm going to regret that decision I made earlier. Well, am I? Let's see. X1 is equal to f of x0 over f primed of x0, like that, plus x0. Except, and I don't know quite why this has happened, but it is to do with this length here. This should be, yes, I can see now what the issue is. This should be minus x1 plus x0. So the difference should be x0 minus x1. And so that should be minus x1 plus x0. And it should be minus x1. And so I'm going to just erase that plus sign and make it a minus sign. So if we continue up here, what we come out with from that is, if we make everything positive or switch the signs of everything, x1 is equal to x0 minus f of x0 divided by f primed of x0. And this is sort of the fundamental formula, except if we make it more general, I'm just going to get rid of the 1 and the 0 here. If we say that this is xn, for example, then this could be here, this would be xn plus 1. Oops, let's try that again. xn and xn plus 1. That's better. So, the Newton-Raphson method is an iteration where we repeat the same calculation several times, and each time our answer should improve. And in fact, as maybe you can see from the diagram at the top, I'm just going to mark this in red, that if this is the root, you notice our first guess is here, second guess, or the improved thing we get, x0, x1, and x2, I have to sort of draw up the side here, is really even closer still. So it actually does a very good job and converges very quickly to the answer. A few points to add about this. So let's just note an advantage. Generally, it's very fast convergence. Disadvantages, there are a couple. We need to be able to differentiate the function. We need to be able to find the gradient. And if we can't find the gradient, then that makes it sort of impossible really to use this method. The reason this method works so well is because if we can differentiate the function to get the gradient sort of points us to a really good next guess on each step. So that's what makes it so fast, but it's also a disadvantage because if you can't readily get the gradient function, then that's a problem. So the other thing is a word of caution. Have to be careful. If you have a situation, for example, like this, with x and f of x, where it's something like this, if you start looking x0 here, then you should be fine, and you should find this root quickly. But say if we were to start here, from an x0 here, then the gradient here is very shallow, and we will end up probably finding a gradient, but we will end up going a long way across. It might mean that we end up, depending on what the function does, I mean, I haven't really drawn the function over here, it could be sort of going, or I don't know what it does, but the Newton-Raphson if you start somewhere which isn't that close to a root, can be a bit unpredictable. So the word of caution is you need to start close to a root, and it's best to have a sketch of the graph, or to have a rough draft printed or something. You really want to understand what's happening. Now there's not much space left on the page. I thought I might try finding the root of an equation, and if we take the example of f of x is equal to x squared minus 5, then clearly the roots of that equation are x is equal to plus or minus the square root of 5, and if we sketch the graph, then what it's going to look like is something like this. So I'm going to say let's start. We'll start, well, if we start with 2.5, so if we have x naught is equal to 2.5, then f of 2.5 is equal to 6.25, and f primed of 2.5, oops, I'm running out of space, I should draw it over the side. Clearly f of x is equal to 2x, so f primed is 5. And so what this means is that if we're going to find x1 is going to be equal to 2.5 minus 6.25 divided by 5. Right, and that is going to equal, I'm just putting it into a calculator here, 2.5 minus 6.25 divided by 5. Then that's given me the wrong answer. F of x is 1.25. It's 2.5 squared is 2.5 squared is 6.25, and then we take away 5, so we get 1.25. And the answer we get out is 2.25 for x1. Now if we do that calculation again, x2 is going to be 2.25 minus, and I just put in the equation here, 2.25 squared minus 5 divided by, well, 2.25 times 2 for the gradient function, f primed of x here is just going to be 4.5. So just put this into the calculator again. So 2.25 squared minus 5 divided by 4.5 and the answer is equal to 2.236 11111, whatever. Now we started at 2.5, we got to 2.25, and now we've got to 2.236. So it looks like already the first decimal place is okay and the second decimal place is going to change. Now I don't have space to write it, but if we do, write it down on the page, but if we do our next iteration, minus, and then put in the brackets 2.236 1111 to the power of 2 divided by 2 divided by 2.236, right? Right, I nearly have the calculation on the calculator sorted. Okay, so the next answer, which comes out, is 2.236068. So we have really got very, very close to a square root of 5 there. And indeed, if we look at what the square root of 5 is, it is the calculator is saying it is pretty much exactly the same as that. So that number there that we've just calculated in the third iteration is good to about 5 or 6 significant figures. Okay, so there is one other thing I wanted to say about the Newton-Raphson method, and that is it's brilliant for finding roots, but let's say that you wanted to find a maximum. Or a minimum. If we know that at a maximum or a minimum, f primed of x is equal to 0. And so what we can do is hunt for roots of f primed of x. And that means we will need f double primed of x. Because effectively then what we will be looking at is a graph of x and f primed of x on the vertical axis, and then the gradients now will be f double primed of x, because we're plotting f primed of x on the vertical axis, so that that's it. So the same Newton-Raphson method can be used not only to find roots but also maxima, using the same formula here that we have.